All right, let's start. Good morning. I'm going to take attendance today. We were working on these more abstract vector spaces. We came up with this axiomatic approach. He had this idea of a field, or more generally a ring, as a set of a number system, let's say, or a metaphorical number system. And once you fix such a thing, you have a vector space. Technically, if instead of a field you have a ring, you don't call it a vector space, you call it a module to sound more fancy, but it's the same idea. And we said for us there are essentially two consequences of this more axiomatic approach. I'm not going to ask you to prove X, Y, Z, whatever, but two things is, well, one of them is that we have these important examples of vector spaces, vectors, linear transformations, things like this, that are not quite of the form Rn or a metric space, whatever. From apps. That's the first consequence. The second consequence is this idea of relativity, namely that somehow we need to be able to talk about things without necessarily fixing a basis. So basis independence, or basis independent thinking, let's put it that way. And of course, as is customary in sciences, thinking about basis independent thinking is pretty much the same thing as, or talking about it is pretty much the same thing as basis covariant thinking. In other words, being aware as to what the consequences are when you fix this basis as opposed to this other basis. Okay, so that's why it's somewhat perhaps better to call it relativity, or basis conscious thinking. Okay. Right, so if I were to give you one object like this, let's say a rod like this, and if I give you two rulers, okay, this is like, yeah, it's this, imagine. I give you two rulers, ruler 1, ruler 2. And with respect to the first ruler, if you measure, let's say 5 as the length, with the other one, if you measure 10, at this stage, you can't quite compare the two. You cannot say, you know, oh, maybe this is whatever. It's like, or maybe with ruler 1, you're measuring one object. With ruler 2, you're measuring some other object. Just by looking at the numbers, you wouldn't be able to say which object you're measuring is longer. For that, you need some sort of a comparison factor, meaning you would need some sort of units here. If the first ruler is in terms of centimeters and the second one is also in terms of centimeters, then you could certainly say that the second object is larger or longer than the first one. Or if the first, well, maybe let's do this like 7 or something. Let's do this 6. We have 6 and 7. Say with the second one, if the second one is in inches, or rather the first one is in inches, then that would be longer. So you need to be able to compare different measurements done by possibly different observers or different machines. It's like a simple example, of course, but the same idea works in general. Thank you. Hey.
I put the whiteboard.
Oh, thank you.
Tomorrow is Tuesday.
Yeah.
But spring is coming, everybody.
That is true.
March, April, and May.
Yes.
Right? After winter.
Yeah.
Okay, have a good day, everybody.
Thank you. Okay. So somehow, if you're collaborating with other people, you need some protocol to be able to convert your measurements to their measurements and vice versa. And so that's the idea of relativity in a sense, but these are like philosophical statements. When it comes to the math of it, things get a little bit more complicated, and that's why we're not going to cover it, or we are going to cover it, or we're going to start covering it, but you're not going to be responsible for it in the second midterm, because I want you to at least have some experience calculating things before asking you questions about it. So change of basis matters. That's sort of the actionable thing in this context when it comes to relativity. Even though we are going to cover it before the second midterm, or at least we're going to start covering it, you're not going to be responsible. You're going to be responsible for it in the third midterm. Okay. So today I would like to mention some ideas. Essentially, even in this more general setting of abstract matrix spaces, most of the things that we discussed so far apply pretty much verbatim. Linear operations, subspaces. Well, there is null space, of course, but you don't call it a null space at this point. You call it a kernel, typically. And it's sort of column space because you don't necessarily have this representation of linear transformations as matrices. Instead of calling it a column space, you call it range or image. So this is kernel. This is image or range. You have these ideas. If you have a set of vectors, you can talk about linear independence of them or linear dependence of them. Or you can talk about a set of vectors and their span. Okay, that's still fine. Well, if you have both, you would call the set basis as usual. The number of things in a basis, you would call a dimension. Kernel is again a subspace, pretty much the same thing as null space, which means that if you look at the dimension of it, you get, as usual, nullity. And likewise, if you were to look at the dimension of the image, that gives you the rank for arbitrary vector spaces, linear transformations, whatever. The only complication here is, well, these spaces could have infinite dimensions, meaning their bases in general are not going to be finite. Okay, so that's a problem in a sense, but still you make do. So here's an example. As usual, this is the nicest example, I think, when it comes to infinite dimensional spaces. We'll see. Curly P is the set of all polynomials with real coefficients. Right, so this is the set of, I'm just going to fast forward this part, AI xi, set of all such expressions. The thing here, of course, is that n is not fixed. So the maximum degree you're not fixing. Okay? You could if you wanted, but at this point you don't need to. You can still add two polynomials of arbitrary degree. And these coefficients are arbitrary also. So n arbitrary, AI's arbitrary also. We talked about how this is a linear, this is a vector space. We talked about some linear transformations on it. So for instance, we said this D, differentiation, is a linear transformation. For those of you who don't remember calculus, in the case of polynomials, differentiation is rather straightforward. Namely, you take an xi and send it to I times x to the I minus 1. And then you generalize linearly, meaning if you were to differentiate something like that, this now turns into this. Well, you start at 1. I from 1 to n, ai times x to the I minus 1. Okay, it's a linear transformation, differentiation. Is a linear transformation, linear operator. Okay. So once you have a linear transformation, you can look at its null space or kernel in this sense, in this case, or column space or image. What is the kernel of D? Null space of D. Well, I'm asking for functions, for polynomials whose derivative is 0. If you know a little bit calculus, you should just immediately say these are constant functions. Okay? But even if you don't see that, how do you open this up? Well, as usual, this kernel is nothing but the space of solutions of dx or dp equals 0. All solutions p of dp equals 0. Okay? And so when you think about that, how can that happen if you have this as p as your vector or polynomial in this case? If this is p, this is d of p. The only way this can be 0, and when I say this, it's the 0 polynomial. So for any x, for any x value fixed, this is 0, I'm saying. Well, the only way that can happen is if all ai's, where I varies from 1 to n, are 0. So you start with a polynomial like this, but then a1, well, ai is 0 for I not equal to 0. All but the 0th indexed coefficient is 0. Okay? Constants. I'll leave it like that. Okay? What's the basis for it? Well, the polynomial that is 1, it's a constant polynomial that is 1. Okay, it's a non-zero vector. And certainly, any constant polynomial is a scalar multiple of the polynomial that is 1. So you can say basis for kernel of differentiation is the polynomial that is constantly 1. Okay? Consequently, the dimension of the kernel of differentiation is 1. It has only one vector in the basis. And therefore, the nullity of differentiation is also 1. Questions?
I was just confusing. What notation is that? The 100 differentiation.
This?
No, up there. Yeah, this one.
Differentiation is a linear operator.
Oh, is. I thought that's a figure. I thought
Oh, no. Yeah. Is. Is a linear operator.
Sorry.
Yeah. That's okay.
Yeah, I understand. Thank you.
No. Apologies. Okay. Any questions or comments about this? Okay. How about the image? So this was differentiation operator. It's null space. What about its image or range? Image, m of d. Right, so these are the all possible outputs that I can obtain by applying d to some polynomial. So I can write it like this. This is the set of all q's, polynomials, such that d of p equals q for some p, for some poly. Okay? Maybe I should ask you, what is the image in this case? Any guesses?
Is it the set of all polynomials?
It's everything. Because there's, calculus, whatever, you can basically integrate the q to get an antiderivative, right? And so if I take a q, some arbitrary vector, q of x is, let's say, I from 0 to n, bi xi. I want some p. I want to engineer some p such that its derivative is equal to q. So I want this to be equal to this. N ai x to the I minus 1. Okay. Now consolidating these terms, and in fact, let's open up the loops here to see it better. Oh, this is with I, 2, 3, whatever. And then n times a sub n, x to the n minus 1. Maybe I should use different indices here, in fact. Because in principle, I don't know that these are going to be of the same index. So let's say m, j, then it's like this, bj, x to the j, goes all the way up to m, like this, and I have that. So I have this expression that works for any x. Okay, that's what it means for two vectors to be the same in this world of polynomials. For any x, you're given this, okay? And now you want to solve this for ai's in terms of bj's.
Wait a minute. The a's not right. Because it should be 2a2x and it's just x. Because it's n.
Yeah, you're right. Thank you. Okay. I think now it works. I meant to open this up. Yeah. So you have this, and you're given that this works for any x, okay? You're not looking for equality for some x's, you're looking for equality for any x, you're given that. You're given the bj's, and you're trying to solve for ai's. Well, you can just consolidate the terms and so on. Right, so you would write it like this: b0 minus a1 plus b1 minus 2a2 x plus dot 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 plus bm minus m a sub m x to the m minus 1 plus minus m plus 1 a sub m plus 1, or sorry, minus m, m, no, I was right actually, plus 1, x to the m, plus dot dot dot, plus minus n, a sub n, x to the n, equals 0. I just sent these terms to the other side. Here I realized, as I was doing this, in order for this to have a solution, ai, well, it has to be the case that n is after m, because otherwise I'm not going to have some terms for an arbitrary thing. And so really, these are going to be 0, of course. This is also 0. And a1 has to be b0, a2 has to be b1 divided by 2, and so on. Okay? So from this, you get that ai is bi minus 1 divided by I. And that gives you a solution. You can take a0 to be whatever you want. If you want, you can take a0 to be 0. This is not super important. The whole point of doing all these calculations is that any polynomial q is of the form d of p for some polynomial. In other words, any polynomial has an antiderivative. That's what I'm trying to do here. Consequently, the image is everything. So image is a whole polynomials. And now you think about a basis. And things are more complicated this time. Okay. It turns out that even though this space has a basis, it's not a finite set of polynomials. Okay? So this is, you see, something that we haven't encountered so far. We were only looking at vector spaces of finite dimension, Rn, or matrix spaces. These are finite dimensional. And we were looking at linear spaces of linear transformations between finite dimensional spaces. That itself is finite dimensional also. But of course, thinking about the shape of a general polynomial, you could say, well, if you were to take all of these monomials, 1, x, x squared, x cubed, whatever, put them all in one set. Now it's an infinite set, but it's a set of polynomials. That would be a basis for P. So let's try to write that down. So S, which is 1, x, x squared, x cubed, dot, 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 xn, dot, dot, dot. This infinite set is a basis for the set of polynomials. Okay? As usual, how do you verify that a set of vectors is a basis? You verify two things: spanning, linear independence. Span is slightly easier in this case. Let's first do that. If P of x is arbitrary, well, observe that I'm already writing a typical polynomial as the span of some vectors in this set. I'm saying take a0 times 1, a1 times x, a2 times x squared, and so on. This is already the typical element in the span. Right? So P is in the span by definition. Span of S by definition. Okay. Does this make sense? This can be quite confusing at this stage, I realize. Right? So even though I write it like this, if you open this up, right? So this is a0 times 1 plus a1 times x plus a2 times x squared plus dot, dot, dot plus a sub n x to the n. Okay. See? These ones are all vectors in my set. These are all scalars. So I'm taking an arbitrary linear combination of vectors in S. So this set spans the whole set of polynomials. So span is OK. How about linear independence?
So doesn't you have an infinite
Yeah,
rank?
yeah, yeah. That's why people would not quite use words like rank and stuff in the infinite dimensional case. They would typically think of rank for matrices. Yeah, exactly. Or they would look at other expressions that somehow often end up being finite. There's something called index, but let's not get into that. So how about linear independence? What do I need to show now? Well, it's kind of trippy to think about this. But now you need to say, if I have some vector in my vector space, well, maybe I should say it like this. If I have finitely many vectors here, okay, I choose finitely many, and I take a linear combination of them. If that is 0 as a vector, then in fact, all the coefficients have to be 0. Say p of x, which is this, AIXI is 0. This is where things get confusing. When I write this, you have to think of it as for any x, okay? I'm not looking at the 0 set of this. For any x. From this, I need to deduce that each of these coefficients are 0. Well, if you're like me, you would do the calculus method, or you would just plug in certain values, or you can use some algebra, okay? If you want to go down the algebra route, you would say, oh, I know the fundamental theorem of, what is it? Algebra, which says that any polynomial has at most finitely many roots. But in order for this to work, for arbitrary x, it has to have infinitely many roots, which means that the only way this can happen is if the polynomial itself is 0. You can do it that way, if you know the fundamental theorem of algebra. If not, this is a slightly more lower level way of thinking about it, which I prefer myself also. What I would do is, well, I would plug in certain x values, okay? Because if this works for any x, that means that I'm allowed to plug in whatever x value I need to sort of simplify the expression to derive certain things. Plug in x equals 0, then p of 0 has to be 0. But when you think about it, p of 0 is nothing but a sub 0. And so I deduce that a sub 0 has to be 0. Okay? Then p of x is a1x plus a2x squared plus dot 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 plus a sub n x to the n. It's of this form. But then, of course, I can factor out the x. X times a1 plus a2x plus dot 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 plus a sub n x to the n minus 1. But we're assuming that for any x, this is 0. Well, that means in order for that to happen, it must be the case that for any x, this is 0. And then you keep going like this. Recursively, a1 is 0, then a2 is 0, and so on. Which finally allows you to conclude that this linear combination of xi's that ended up being the 0 vector ultimately was nothing but the trivial linear combination where all coefficients are 0. Okay. Now, as you see, in this world of polynomials, even though we're somewhat using linear algebra, the flavor is somewhat different. Okay? You need to sort of factorize polynomials, whatever. And if you're not familiar with these ideas, it might be kind of daunting. I realize all that. Okay? Any comments or questions about this so far? Does this kind of make sense? How many of you feel kind of lost here? A couple of you. Okay. Yeah, like things like, tricks like this are not really the main concern of this class. So we talked about linear operators, subspaces, kernel, image, these two, this. We did all of it. Okay, good. I'll say this, even though these monomials is sort of the standard basis, so to speak, for the space of polynomials. When it comes to applications, there are other bases that are also very important. Maybe in the next problem set I'll put some examples of that. So for instance, if you're interested in computer graphics, there are things called Bézier curves there. And Bézier curves are essentially functions whose graphs are made up of, well, graphs of finitely many polynomials of bounded degree. And to think about Bézier curves, often use a different basis that is more compatible with what you're trying to do. So here's a nice application of all this stuff. Interpolation, polynomial interpolation. Okay. So example. Polynomial interpolation. Let's say you're given 2 points on the plane. Let's say this point and this point. Say this is 1. Well, let's do 0 to 1 actually. It's easier. Zero, 1. Say you're given 0, 1/2, and then 1, 1. You're given 2 points, 2 control points. Well, if you're given 2 points, I hope you would agree with me that there's a unique line passing through both of these points. Right, so linear interpolation would require that you come up with this guy. How do you find the variables, the numbers associated to this? Well, you would say this is y equals mx plus b. Right? M is supposed to be the slope, and b is supposed to be the, y-intercept. And in a sense, you can think of this as a degree 1 polynomial. So p of x equals mx plus b, if you want. I'll write it, in fact, in polynomial form. P of x equals a0 plus a1x. You want to find the numbers a0 and a1. Okay? And how do you do this? Well, you say, there are multiple ways of doing this, of course, but let's try to come up with an example with a method that is compatible with linear algebra so that it is clear where linear algebra comes into play. Because in a second, I'm going to give you more points, right? You would say, well, this polynomial has to pass through these 2 points, which means if I were to plug in x equals 0, p of x has to be 1/2. So 1/2 equals p of 0, but then when you plug this in, you get this. Okay, and 1 equals p of 1, and when you plug this in, you get a0 plus a1. Okay, now this gives you a system of 2 linear equations with 2 unknowns. Okay, that's nice because at this point we know how to solve it. Right, so you would put it like this, a0, a1, and then 1, 0, 1, 1. Okay, you're trying to solve this system. That matrix is invertible, AD minus BC is 1, send it to the other side, and in fact this is a shear, I can immediately compute the inverse. It's this, right? Lower triangular, it's a group, it's a matrix group. Inverse is of the same form, The only thing is that you put a minus there. 1/2, 1, and this gives you 1/2 here, and then 1/2 here. Meaning, this polynomial you need is p of x equals 1/2 plus x over 2. When x is 0, it's at 1/2. When x is 1, this is 1/2. This is also 1/2. It also satisfies this other thing. Okay. Now, certainly in this case, you can reduce everything to Rn's whatever. But in certain situations, it also helps to think about this space of polynomials in general. Any comments or questions about what I did over here? Yeah.
How did you get from the 1 equals p of 1 down to the 1/2 1? Yeah, from there to
Well, this is equal to this, and this is equal to this.
down to the matrix.
Two numbers. Two numbers.
And then how'd you get the 1 0 1 1?
Okay, write these on the other side.
Okay, I see.
Yeah. Of course, in this case, it's not that important to do this. You can just do it by hand, whatever. And probably you did learn how to get this equation without using linear algebra. But of course, now I'm going to make things more complicated. Say I give you 3 points. If I were to give you 3 points in the plane, now you're not guaranteed that there's a unique line passing through it. I mean, either there's a unique line or there's no line passing through all 3. Right, so let's do it here. So this was the first interpolation. Say now I do this. Poly of, so find the poly of degree at most 2. The poly at most 2 such that, say the polynomial is called p. Its graph passes through, let's say, no, these 2 points, and then I'll give you one more point. Let's take 1/2, 1/2. Okay. Now I'm asking you to fit a parabola into these 3 points. Okay. So I would imagine this, if you want to be intuitive about it, I would start with a horizontal line, and I would sort of start curving it, and then sort of I would estimate it this way. Imagine a horizontal line passing through this. Look at x equals 1/4. Start pulling this horizontal along x equals 1/4. Here's what I mean. Start with this. Okay. Imagine this blue line is variable. You can bend it, imagine. But you can only bend it around here. Okay. These 2 are hinges, imagine. Okay. I'm going to pull this down. As I pull this, I'm imagining that this blue line starts sort of folding as a parabola. And certainly, as this keeps folding, eventually I'm going to hit this point also. Okay, so this. Do we see this? This is the intuition, of course, so it's specific to these 3 points. But how do you do this algebraically, and how do you come up with the explicit formula? Well, you again write down the equations. And in fact, I'll do it this way. Okay, so this is so x1, y1. This is the first control point. This is the middle control point. x2, y2. And this is x3, y3. Okay. Now I'm looking for p of the form a0 plus a1x plus a2x squared. Trying to solve for a0, a1, and a2. I plug these in, gives me this. In terms of matrices, right? So this is supposed to be a0 plus a1x, 1 plus a2x, 1 squared. Okay, and then a0 plus a1x, 2 plus a2x, 2 squared. And then a0 plus a1x, 3 plus a2x, 3 squared. I just used the idea that this polynomial has to pass through all three of these points. But of course, this right-hand side is nothing but the matrix vector multiplication. My unknowns are a0, a1, and a2. And so here you get this Vandermonde matrix that you're looking into, I think, or you were looking into in one of the previous problem sets. Okay. There's no squared here. You worked on a problem. You worked on a problem in a previous problem set where you computed the determinant of a matrix of this form. Namely, the determinant of this is non-zero if and only if x1, x2, and x3 are pairwise distinct. Okay. Meaning, insofar as these 3 x values are distinct, this is invertible, which means that there's a unique solution. Okay. I'll write it here. So this is Vandermonde. Let's call it A. A is invertible if and only if its determinant is non-zero. And I don't quite remember the formula with the plus and minus, but I know that insofar as x1 is distinct from x2 and x3, and x2 is distinct from x3, the determinant is going to be non-zero. Which in this case certainly is, which means this has a unique solution. Of course, you will need to compute the inverse of this matrix to do this calculation, but I hope you would appreciate the value of such a formula. This formula immediately works for any 3 numbers any 3 points on the plane, gives you immediately the coefficients of the parabola that interpolates these 3 points, insofar as, of course, the x values are distinct. Okay? And of course, you can do this more generally. You can take n points. If you were to take n points, right, on the plane, you would need a degree n plus 1 polynomial. There would be a unique one. And there would be at least one polynomial of degree higher, in fact. So there are things like this. And so it ends up being useful to be able to think about vectors or polynomials as vectors and so on. Okay. And of course, what this leads to is this idea that, well, when it comes to calculations, even though my vector could be from an infinite dimensional space, maybe in terms of calculations, things sort of like reduce and I'm left with a finite dimensional vector. Well, in this case, you see, instead of thinking about this polynomial as a vector, well, I just reduced it to this. I said, okay, so this is complicated for me to think about, so I'm just going to think of this tuple of numbers, right? This is a vector in R3. This is a vector in P. And we did calculations with this vector in R3. Now, technically, these two things are not exactly the same. Their types are different. Right? This is a function, this is a vector. But in a sense, they are related. And so what it is that this is the matrix representation of this polynomial with respect to this standard matrix, standard basis. So, matrix rep of P of this specific vector relative to that basis over there. Okay? So next time we're going to start talking more about this relativity. Thank you. All right, let's start. I'm out of breath. Good morning. Today we're going to start talking about this relativity business. Kind of gets confusing, I think, even at a conceptual level. So I'm going to take my time. We're going to slow down, really, because even though it's a confusing idea, it's very important that you understand this. So first, we need to talk about matrix representations of vectors to begin with. So far, we've been thinking about vectors as always ultimately matrices, column matrices. We're going to put on our straight jackets, okay, for a while. We're going to pause that understanding for a while. And we're going to sort of separate vectors as things that really are not matrices, even column matrices. And then we're going to talk about this representation of, or this idea of representation, namely, how do you take a vector and store it in a matrix? Okay, I want to separate these two ideas. And once we understand that, probably I'm going to spend all of today with this idea, do a bunch of examples. Then we're going to transition, probably tomorrow, to this change of basis matrix. Okay, so first, here's a theorem that is given in the textbook. I'm not going to state it exactly the way it is stated in the textbook, but these are the way I'm going to state it is also correct. It is what is called the unique representation theorem. If you have a vector space V and a set S of vectors, then S is a basis of V if and only if something, okay? This is characterizing for you what it means for a subset S to be a basis for the vector space you chose. Essentially, I want to say S is a basis if and only if any vector in V can be represented.
I cleaned the whiteboard.
Oh, thank you so much.
You're welcome. Tomorrow is Wednesday.
That is true. Thank you. So ultimately, it's going to say S is a basis if and only if any vector in V can be represented uniquely as a linear combination of some vectors in S. Okay? One thing that is important here is that even though S itself could be infinite in principle, in our world, we always want to be able to use at most finitely many vectors in S to represent any given vector. If you sort of start incorporating more calculus into the mix, then you start talking about infinite series, but that's a different type of a basis. That's not what we're going to look into, okay? So if you want to be more explicit, well, I mean, finite basis is a different thing. So I'm going to leave it like this. For any v and v, there is a unique positive integer n a unique n tuple of vectors in S, a unique let's say set of n vectors in S, and unique numbers C1 to Cn, a unique set of n possibly repeating and scalars let me say it like this perhaps. Say S1 to Sn. These are vectors in S. Scalars C1 to Cn such that V is the associated linear combination. V is C1 times S1 plus C2 times S2 and so on. Do I want to say? Probably, I want to say not equal to 0. Okay. I think now it works. Yes. You can just take this for granted. How do you, if you want to sort of justify this, how would you do this? You would start with a basis. Well, one part tells you something about the fact that any v is in the span of that set S, and uniqueness tells you if you have two representations, you could rearrange them to get linear independence and so on. It's not very important how to sort of prove this. Let's just take it for granted. I think it is fairly believable. Now, for what is to come to make sense, we really need to put the straitjackets on, okay? So, until further notice, by the end of this, until the end of this course or this class, no shenanigans with, oh, I can take this vector and I can think of it that way and whatever. Okay, for now we're doing this because otherwise things do get very complicated. So, no, I can think of this as that. Etc. Okay. In other words, I want to be very careful with the types of objects that I'm dealing with. So when I'm given Rn, technically its definition is it's a set of tuples. Okay? So I'm going to be very specific about notation. So you want to hard code the types. The types of objects, if you know what this means. Okay. Rn, okay, let's start with R. Let's start with, let me think. I want to start with R. It's easier. Okay. Now, R is the field of scalars. If I'm thinking of R as the field of scalars, its elements are just going to be numbers. As the field scalars, any element is a number, is a real number. Okay, but I can think of R as a vector space also. Okay, in the sense that I can think of the space of 1 by 1 matrices. If I'm thinking of R as that, I'll write it like this. If I'm thinking of R as a space of 1 by 1s, okay, the elements in this set of 1 by 1s is of the form open paren, put number n, close paren. As vector space of 1 by 1 matrices, any element, any vector here is of the form open paren, put some number in, R, close paren. Okay, I'm going to be very specific about notation for a while. R, some arbitrary number. I should add this here. There's no, how to say, there's no problem with thinking of R as a vector field, a vector space of one dimension also, or 1D vector space. So these two are one thing, this is one thing. So what I'm going to try to do is, I'm going to try to store my vector, which is a number, into a matrix. I want to store vector in R, or maybe I should say R to the 1, in a 1 by 1. This is what I want to do. I want to store it. The standard way we did it was by saying, take the number 2, let's say, whatever, put it into the 1 by 1, open paren, 2, close paren. But this, in a sense, depends on the basis, choice of the basis. Now, if I were to ask you, if I were to think about R to the 1 as a vector space, what are its possible bases? It is one-dimensional. Any basis in R to the 1 has to have exactly one vector.
It would just be like the natural numbers, right?
All non-zero numbers.
Yeah.
Yeah. So 1 is a basis of R to the 1. 2 is a basis. Minus 15 is a basis. Pi is a basis, whatever. Okay? So in a sense, the way you should think about this is, this R to the 1 is something, it's an object where only the origin is marked. Okay? then you choose your units, okay? Choosing a basis here corresponds to choosing a unit, essentially. If you're measuring in terms of centimeters, here's 1, okay? This is 1 in terms of centimeters. If you're using inches, okay, it's over here, perhaps. This is 1 in terms of some other thing. Okay, so 1 centimeter is here, 1 inch is there or there. And so depending on which ruler you use, you store a different number in the matrix that represents your actual number. Okay? So, any basis of r to the 1 is of the form, well, S, right, open curly braces, set notation, and put some, let's say, U for unit, close paren, U non-zero. For some other situation, you may want to choose your basis to be -1, right? Any number can be written as a linear combination of this specific U for any U. Things are getting complicated. It's getting confusing, okay? So fix a basis. Okay. Now, to store whatever number, whatever vector in R to the 1 in a 1 by 1, what you need to do is you need to take that arbitrary vector and write it in terms of this basis you chose. Then for any, let's say, R in R, since R equals, well, R divided by U times U, okay, this I'm thinking as the vector, this I'm thinking as a scalar. So this is a linear combination. Write it. I realize this is getting confusing. It's a confusing matter. Think of this as the vector. Think of this as the scalar. Take your vector, write it, expand it in terms of the basis you chose. Now these coefficients you store. That you end up, the matrix you end up with is the matrix representation of the vector relative to this basis. So I'll write it here. Rep of R relative to the basis U is the number R divided by U put in the 1 by 1. It's a 1 by 1 matrix. Okay. And so to represent this idea, this fact that this is the matrix representation of R relative to the basis that contains only U, I think in the textbook there's a different symbol. Maybe it's something like this, I think. Let's do this. Let's put the vector, put in brackets, and put a U over there. Something like this. Take your actual vector, expand it relative to the basis you chose. That gives you a bunch of numbers. Store those numbers in the 1 by 1. So in a sense, this is kind of doing some sort of a dimensional analysis, or unit conversion in a sense, or it's just keeping track of the units in one dimension. Just to give you a numerical example, of course, 5 represented with respect to the standard basis, which is just the number 1, is nothing but this. Okay, just divide it. Okay, this is what we've been using so far. Okay, but now we're saying, oh, this conversion between vectors and matrices is relative to a certain basis. We're being more conscious about, more explicit about what the basis we're using is. This is what we've been doing so far. Okay. But for instance, if I store the same vector, same r, relative to this other basis, let's say 5. 5 itself is a basis. Now I would store it as a 1. Okay. Or if I were to store 5 relative to -1, now I would store it as -5. So you see, we're splitting the vector from how it is represented. And like I said, the way I try to make sense of this in my mind is, well, I have a physical object. Physical object is my vector space, and different bases correspond to different rulers. Okay? You use different rulers to measure the length, and possibly you get different numbers based on what type of a unit each of these rulers use. Okay? The length is something out there. I don't have control over it. But what I call that vector in terms of numerics, that depends on how I see it. Does this kind of make sense? Or, you know, if you have glasses too, it's like you can think of it that way. It's like me sort of taking off my glasses does not change the world. You're still the same, but you're more fuzzy for me. I put the glasses on. The glasses is the basis. If I put on sunglasses, that's a different basis. Makes certain things nicer, perhaps, but inside, perhaps, makes it harder to see. Okay? So depending on the application, you quite possibly choose a different basis for the thing you're trying to do. Or another way to think about it is, well, you're in a house, let's say, you have a window, you're looking out. Okay? What is happening outside the house is the vector space. The window itself is the basis. Maybe it is like, you know, frosted glass, whatever. Depending on the situation, depending on what you're trying to do, you get something else, right? So your basis could be different. Just because you sort of tint the glass, the windows on your car, doesn't make the outside any different. It's just that things look different. So the basis is how you perceive things, and what things are is something beyond that you don't really have control over. Okay, let's keep going. Let's do it in 2 dimensions. And so you see this, what I've been referring to as this change of basis, is essentially a protocol for you to say, oh, I look at the world, I see this. And you talk to someone else, that person sees, even though they look at the same thing, they see something else compared to what you see. And so you need a conversion factor. Change of basis is essentially that. So let's do this. Here's another example. R2. Okay? Now, I don't want to think of this as a space of 2 by 1s. Okay? So that would be m of 2 times 1. When I see this, I want to think of this as the space of pairs of numbers. So any vector in R2 is of the form x comma y for two numbers, two scalars x and y. And y. Okay? I'm not going to allow myself to immediately say, oh, this is the same thing as the 2 by 1 xy. I'm not saying that for now. I'm putting on the straitjacket, okay? I'm saying this is how vectors in R2 are presented. I'm hard coding the types. I don't get to move the symbolism around. Otherwise, it gets confusing. Let's look at this. So in this notation, I'll use a lowercase sigma for standard. I want to write down the standard basis. I cannot write 1, 0, 0, 1 because those are not the types of vectors I'm looking into here. So I need to write it as 1, 0 and 0, 1. Okay? And in fact, maybe let's put it like this. So this is ordered. First vector in my basis is this. Second vector is this. Order matters. Order of vectors matter here. Now to store an arbitrary vector here into a matrix, all I'm going to do is I'm going to take this basis and write this vector in terms of basis vectors. So, okay, this is x times 1, 0 plus y times 0, 1. Okay, took my arbitrary vector, I expanded it using basis vectors relative to the basis I chose. Now I have a bunch of scalars. Those scalars I'm going to put in a 2 by 1, and that's going to be my matrix representation. So xy, bracket, and then here I put the sigma to represent. I'm going to write the matrix that is relative to this specific basis. Which is xy. Again, this is what we've been using so far. The reason why we were calling something like this the standard basis was because underneath the hood, we were always doing this conversion, and it was always relative to these standard bases that we were using. Here's another example for the same space. And I'll do, in fact, one more. Let's do the diagonals. Say tau is 1, 1 and 1, minus 1. That's another basis. Now, the question is, if I were to take an arbitrary vector xy, okay, it's a pair of numbers, what is the matrix representation of that arbitrary vector with respect to this basis? Well, xy equals, I want to say, a times 1, 1 plus b times 1, minus 1 for some scalars a and b. I set this up, this linear combination equation, and then I'm going to solve for a and b. Scalars a and b, maybe I should use lowercase actually, so that we don't think of these as matrices. lowercase a, lowercase b, a and b. And then once I have the solution to this, the matrix representation of xy relative to the tau basis would be AB. Okay, so we need to solve this equation for A and B. And how do you do this? Well, you just consolidate the terms. A minus B. This pair is equal to this pair. In order for that to work, x has to be equal to a plus b, and y has to be equal to a minus b. Now, this is a system of linear equations, which means you can store it in a matrix. Like so. Send it to the other side, because this is invertible. AB is, well, xy multiplied by the inverse of this. How do you compute the inverse of such a thing? Well, you change the orders of these, and then you put minuses there. And don't forget to divide by the determinant. The determinant in this case is minus 1, minus 1, minus 2. So you need to divide everything by minus 2, which means this is going to be like this, like this, like this, like this. Meaning, A is, well, the average of x and y, and B is the average of x and minus y. So that to be a little bit more specific, let's look at some numerical vectors. So for instance, 1, 0 relative to sigma would be stored as 1, 0. So one zero relative to tau, this time would be stored as 1/2, 1/2. Okay. And 1/2, 1/2 relative to tau would be stored as 1, 0. Yes. Yes, that is correct. 1/2. No, hang on a minute. This is the average, 1/2 divided by 2, by 0. So 1/2, 0. Just plugging in the numbers. Just taking the average. It's very confusing. So in this world now, when people ask you what is the matrix representation of this specific vector, the proper answer now is who's asking, right? With respect to what? So ultimately, you get to now say, well, it depends. It depends on something. It depends on the choice of how you see the vector space. This is really confusing. Like if you're feeling sort of shaky a little bit, that is perfectly normal. This is, even though it's not very sophisticated in a sense, mathematically, it is very confusing conceptually. Because everything is now relative. Questions or comments about this? And you see, even though we did put on the straitjackets on, once we have this equation, and then we rewrote it like this, we realized this is a system of linear equations, but somehow, once you have sort of a contained environment for linear algebra calculations, even though at large we were not using matrices and so on, you can still use everything we learned so far to calculate things. Okay? So the way I imagine this is that, it's like a Pokemon game in a sense. It's like you move around and whatever, and then every once in a while you come across a trainer, and that's sort of like a different environment. So calculation is sort of like those Pokemon fights. Walking around, and it's like you encounter a wild Pikachu, whatever. And then you sort of do your linear algebra calculations, you figure something out, and then you move on with your more abstract looking considerations. Now let's try to make sense of this geometrically as well. What is the significance between looking at sigma or tau? Well, in a sense, sigma, the standard basis, corresponds to this idea that we're always using the horizontal and the vertical axes to write numbers, to put numbers to any vector. So R2 with specified basis sigma, well, it would look like this. Okay. On the other hand, R2 with basis tau, well, it doesn't look like this anymore. Now, for some reason, it looks like this. This is the coordinate axes you're using this time. So that, for instance, if you were to look at 1, 0, okay, 1, 0 is here, and it's also here. So 1, 0. Relative to sigma, the fact that the matrix representation of the vector 1, 0 is the matrix 1, 0 tells you now that, well, from the perspective of sigma, to go to the 1, 0 vector, move 1 unit in the first vector for sigma 1, and don't move in the second vector in the sigma basis. On the other hand, for tau, it says to move to 1, 0, move 1/2 units in the first vector direction for tau. So move 1/2 units in this direction. So this is this. Yes, and then move 1/2 units in the other direction. I feel like I'm making a mistake somewhere. This is 1, 1. This is 1 minus 1. Maybe I made a mistake in the calculations. So 1, 1 points that direction, 1 minus 1 points in that direction.
And yeah, down. It should be in this way, I thought.
Oh, yes, yes,
Yeah.
yes.
Yeah.
Okay, this is, okay. Let's be a little bit more clear then. 1 comma 1. This is this. This is in this direction. 1 comma, oh, okay, okay. Very good, thank you. I put the arrows wrong. This is 1, 0. Says move 1/2 units in this direction. Okay, and then move 1/2 units in the second vector direction. Okay. So that's a sort of geometric correspondence. Any comments or questions about this? The notation in the textbook could be different, by the way. I don't quite remember the notation in the textbook. I tend to use this notation, in fact. The notation I like is this. Okay. Oh. I would write it like this. Beta is a vector here. M sub beta is a transformation that takes your wild vector and turns it into an n by 1. Is the matrix representation of the vector B relative to the basis beta. I like this notation because, well, M sub beta, this transformation that associates to each vector its matrix representation, itself is a linear transformation. Okay? In fact, it's an invertible linear transformation. So I keep using the same notation. It's literally the same thing in a sense. Yeah, so if you want to be using this notation, you would write, for instance, this is m sub sigma of 1, 0. This is m sub tau of 1, 0. This is m sub tau of 1/2, 1/2. For instance, this is m sub 5 of 5, and so on. Matrix of this relative to that other thing. Any comments or questions so far? Let's do a slightly more complicated example. Yesterday we came up with this idea of, well, taking a polynomial and storing it in a column matrix. Well, essentially we're using the same idea here. Okay? what I'll do is I'll look at a certain subspace of all polynomials, namely polynomials of degree at most n. Say P sub capital N. This is the subspace of the space of all polynomials of degree at most n, upper bounded by n. Okay? If you were to add two such polynomials, you would get back yet another polynomial of the same degree bound, and likewise with scalar multiplication as well. So this is a subspace of all p, all polynomials p. And if you want, you can think of it as the kernel, which is essentially the same thing as null space, of differentiating how many times? N plus 1 times, whatever. So degree 0, if your degree is upper bounded by 0, this is the space of constant polynomials. Yesterday we showed how this is the same thing as the kernel of differentiation. Okay. So it should be one more, which means this is the kernel of differentiating n plus 1 times. What does this mean? It means if I have a polynomial that I know for sure that its n plus first derivative is 0, then its degree cannot be more than n. Okay. For this, we have this standard basis. And in fact, let's choose n to be 2. So I'm just looking at quadratic polynomials. So a0 plus a1x plus a2x squared. These are general vectors in this subspace or polynomials. Standard basis, sigma, is 1x x squared, maybe like this. Well, then any polynomial like this is going to look like this. I'm storing this polynomial, it's a wild vector in my wild vector space. I'm storing it in a 3×1. Next to 1, I see a0. So this is a0. This is a1. This is a2. Okay. If you want to be sort of fancier with your notation, what you could do is you can just start with one polynomial. Like so, and realize these AIs are nothing but the Taylor expansion coefficients of P. So for instance, P of 0 is A0 differentiates A1 plus 2a2x, which means P prime of 0 is A1. Differentiate again, P double prime is 2a2, which means P double prime at 0 is twice a2. Meaning, the matrix representation of a polynomial relative to the standard basis is P of 0, P prime of 0, P double prime of 0 divided by 2. Taylor expansion. Okay, so somehow this matrix representation business for polynomials relative to the standard basis, what it does is it just takes your polynomial, expands it in the Taylor sense, if you're familiar with that, and stores those coefficients, the Taylor coefficients at 0. Okay? Make sense? But depending on applications, you may want to use a different bases. And like I said, probably in the next problem set, you're going to see different bases. A nice basis, for instance, here's another basis. I need to look it up. I think if I try to write it out, I'm going to have issues. But essentially, I'm going to look at polynomials of this form. X to the k, 1 minus x to the n minus k. These are what I call the Bernstein polynomials. Somehow, these are related to these Bézier curve stuff that is very useful in computer-assisted graphics and so on. Okay, that's it for today. We're going to continue tomorrow. Thank you. All right, let's start. Good morning. So, small change in plans compared to the tentative schedule on the syllabus. I think I'm not going to spend as much time as I was perhaps hoping to in terms of, so for the ideas related to digital signal processing, DSP. So we had this space of signals. I think what I'm going to do is maybe we're going to take some time on Monday discussing certain ideas. At the very least, I would like to talk a little bit about these things called linear time invariant filters in the context of DSP. Another thing too, I'm going to do a couple examples again today regarding matrix representations of vectors, but I think I'm going to leave this change of basis business to Monday. Today what I'd like to do is, well, give you some more sort of stuff related to consequences of this axiomatic approach. We have some terminology that is used in the textbook. And I also want to do some sort of a review for the midterm on Friday. Okay. So let's first talk about this linear isomorphism. It's a sort of scary sounding word, isomorphism. It means a linear transformation that is invertible. Okay, so if I have two vector spaces V and W, a linear isomorphism from V to W is a linear transformation that has an inverse. Okay. Linear isomorphism. Okay. From V to W is a linear op, let's call it T, from V to W that has an inverse transformation. So how can we say this? In this general context, we can't quite talk about like the dimension of the column space or whatever. So we can't quite talk about rank. But we can certainly talk about what it means for a linear transformation to have an inverse linear transformation. Such that there is a linear op, which of course people would denote by t to the minus 1, that goes backwards. Such that, well, if you take the composite of these, right, so take a vector w in w, first apply t to the minus 1, now you have a vector in v, so this you apply t, you want to get back your original input, and you want to do it the other way around, like this. That's a linear isomorphism. If there is a linear isomorphism between two vector spaces, and there might, it might well be the case that there are certain spaces where they are not isomorphic, well, you call them isomorphic vector spaces. Isomorphic, meaning in simple English, pretty much the same. Okay. If there is a linear iso from V to W. Okay. For finite dimensional vector spaces, we have this wonderful classification theorem. And it says that this integer, that is the dimension, is the only invariant that you need for isomorphism. In other words, classification theorem says that for finite dimensional vector spaces, are finite dimensional, so you don't get to use this theorem, for instance, for polynomials, whatever. Then V is isomorphic to W if and only if their dimensions are the same integer. Then V is isomorphic to W. So this is the symbol for isomorphism. You put an equality and then a tilde on top of it. And there's like common notation. They're not exactly the same, but they're pretty much the same, right? If and only if their dimensions are the same. And there are certain contexts where people would not put this tilde on top. They would just take two vector spaces to be the same if the dimensions are the same. Okay, so just to give examples, of course, what you can say is, well, these are all isomorphic. R to the 6 is isomorphic to the space of 6 by 1 matrices, which is isomorphic to the space of 3 by 2 matrices, isomorphic to the space of polynomials of degree at most 5. These are all 6-dimensional. Let's add one more, perhaps. This is also isomorphic to the column space of a matrix of rank 6. Okay, I'll just do this. 6, then 0, like this. These are 0, whatever, they're all 0. You can take a matrix like this that has rank 6. Dimension, in other words, rank in this case, is 6. rank is the same thing as the dimension of the column space. Okay, if this is 6-dimensional, these are all the same. It's isomorphic, you see. So you want to say, another example. So if I were to take this is the span of E1 plus E2, okay, in the plane. And if I were to look at the span of E1 minus E2, okay, both of them are lines. They are both one-dimensional. So even though they are not exactly the same space, they are isomorphic spaces. Okay, people would write it like this. Okay. So, for instance, in computer science, there's a distinction between type and token. Isomorphism is about the type. Okay. Token is a specific instantiation of the type. Technically, these two lines are distinct tokens, but they are the same type, in a sense. So they are not exactly the same spaces, but they are isomorphic spaces. Okay, maybe I should write that. So not exactly the same spaces, but isomorphic spaces. So this means different tokens, if you know what this means. And this means same type. Type and token. Okay. Depending on the context, you may want to keep track of the specific token, right? So if I give you a matrix, if I ask you to compute a basis for the column space, now you really need to worry about the specific token, how it is positioned in the image, or rather in the output space. But if I ask you, what is the rank of the matrix? Well, I'm just asking for the type in a sense in that case, because I'm just asking for the integer. Okay. Any comments or questions about this stuff? Okay. Okay. The idea of an isomorphism, you see, works in infinite dimensions as well. But the classification theorem doesn't quite work. There are classification theorems for infinite dimensional spaces also, but they are harder to state. They're beyond the level of this class, so we're not going to talk about that. What I want to do is I want to go back to these polynomial spaces and talk a little bit more about matrix representations. I'll erase this. And even before that, let's go back to the plane case. So I wanted to mention something. This is, again, the space of all pairs. Okay. Scalars, xy scalars. So the standard basis is sigma 1, 0 and 0, 1 as pairs. Okay, let's write it like this. So the order matters. Okay. And so based on this, the matrix representation of a pair of numbers, right? So this is how a vector is given to me, is just xy. So if I'm trying to represent xy as a matrix, right, so M sub sigma, the matrix representation of the vector xy relative to the standard basis is the 2 by 1 xy. By the way, in the textbook, this notation, instead of writing it to the left, they write it to the right, I think. So they write it like this. In the textbook, this is the notation, I believe. Although to me, the notation in the textbook is somewhat confusing, so I'm just going to keep this M notation. OK. And then we looked at this diagonal guys. And in fact, let me do this. Let me flip the orders of these two. OK? Now, when I write, instead of the curly braces, if I use open paren, close paren, that means the order of the vectors matter. So in a sense, this is a tuple of vectors. When you're writing tuples, the order matters. So if you look at, let's say, sigma prime, same vectors, but written in a different order. Okay, it's a different basis. And if I were to look at the matrix representation of xy relative to sigma prime, I would get yx, for instance. Why is that? Because how do I get these coefficients? Well, I take my vector xy, expand using the basis vectors, and since now 0, 1 is the first vector for sigma prime, the scalar associated to this, which in this case is going to be y, has to go into the first entry. Okay, so the order matters. Sometimes the order doesn't matter for certain situations. Sometimes it does matter. So that you end up needing to sort of figure out from the context. OK. And then we had this tau basis. This was 1, 1, 1, minus 1. And in fact, I'll do one more. Tau prime, say 1, 1, and then this multiplied by negative 1. In other words, minus 1, 1. These are 4 distinct bases, ordered bases. And I believe we computed the matrix representation relative to tau yesterday. What was this? This was, first you take the average of the entries, and then you take the average of x and minus y. OK. Let's again try to figure out the matrix representation. We can sort of try to move this around a little bit, engineer it or reverse engineer it to get this. But let's say that we forgot, and then try to recover it again. So you see, to get this matrix representation business, to do it properly, you need to be very careful with your basis vectors in the order they were given to you. They're given to you. OK. So I want to compute the matrix representation of an arbitrary vector xy relative to this tau prime. I'm trying to compute this. So for this, I'm just going to write it here. Start with the xy. OK. Maybe I should change this just a little bit more, actually. Let's leave it. That's OK. So I look at my tau prime, okay? First vector plus second vector minus 1, 1. And here's going to be C1, here's going to be C2. I set up this equation first. I'm thinking x and y to be given, and I'm trying to solve for C1 and C2. Given x and y, solve for C1 and C2. How do you do this? Well, you just consolidate the terms. Right, so this is, let's take our time this time. Scalar multiply plus minus C2 comma C2. How do I add two pairs? Well, you add this to this, this to that. So this is C1 minus C2 comma C1 plus C2. Okay. In order for this pair to be equal to this pair, it must be the case that x is equal to C1 minus C2 and y is equal to C1 plus C2. Okay, now I have a system of two equations with two unknowns, which I can solve. At this point, for instance, you can add these two to get rid of the C2s, whatever. But I hope you would appreciate in higher dimensions, doing this, solving the system kind of requires, or it becomes easier with linear algebra. So let's just use linear algebra to solve it. I'm just going to store it in matrix form. Okay, 1 minus 1, 1, 1. C1, C2. This has determinant plus 2 this time. So it is invertible. Determinant not equal to 0 means invertible. Write it here so that we're kind of starting to do the review also. Has an inverse. So this has an inverse. I can send it to the other side by essentially taking this and left multiplying both sides by the same matrix inverse. Right? So C1, C2 is 1 minus 1, 1, 1 to the minus 1 xy. You need more space. Like so. What was the rule to invert a 2 by 2? Let's remind that as well. Remember, if I have this, okay, the end result is going to be a 2 by 2. It's going to be a 2 by 2. And then I'm going to scale it by some number here. That's how I imagine it. And what was the rule for 2 by 2s? Well, you flip A and D. So instead of A, now I have D. Instead of D, now I have A. B and C are fixed, but you put minuses in front. So now this is minus B, this is minus C. Okay? And here is the number which is AD minus BC, the determinant. Okay, this was the rule for 2 by 2s. For higher dimensional matrices, inverses are kind of harder to keep track of in a sense. Even though there's a formula, I would not recommend that you remember it. Okay, so I'm just going to apply that rule to here. So x, y stays the same. Now I'm going to apply this rule over here. A and D are 1, so they stay. This is plus, this is minus now. Okay, and then I need to scale. What is AD minus BC? AD minus BC is 2, so 1 over 2. Okay, multiplying these gives me that C1 is the average. Okay, C2 is minus x plus y divided by 2. Okay, so that the matrix representation, okay, of a typical vector xy relative to tau prime is the 2 by 1 whose entries are C1 and C2, and those are those. Okay, I'll write it here. So this is C1, C2, which is average, and then minus x plus y divided by 2. So just write it explicitly. Again, matrix rep of the vector xy relative to the basis tau prime. Okay? So you see, even though I look at the same vector, depending on how I look at it, the outputs end up being different. Okay? Relativity. How I'm imagining this is, well, this xy is a sort of real thing. It's somewhere out there that I don't have control over. And these bases are, if you want to be more physical, you can think of them as inertial frames or your measurement apparatus. Okay? You have sensors or whatever. So bases are frames or coordinates or sensors or measurement apparatuses or whatever. And so you measure what is out there relative to something. It gives you a bunch of numbers. Okay? But even though you might be observing the very same thing, depending on how you're observing it, you might end up getting different measurements. Okay? So I'll write this as well. Just saying here, so this is something out there. It's real, okay? And this is my measurement. Okay. Any comments or questions about this? Yeah.
Is this going to be on this turn, like on this exam?
No. But we need to cover it at some point, and yeah. Yeah, I mean this. I mean, when I was first learning this, when I was first learning this stuff, to me this was like very confusing. Do you sort of think the same? I was like very confused about this business when I was first learning it. So that's why
I
I'm.
feel like we need a little bit more practice.
Yeah, that is true. Yeah, you need to calculate a bunch of things. I agree. That's why I don't want to sort of rush it. Okay. Okay, let's do one more example with this for polynomials. Yesterday I mentioned, even though these monomials are kind of nice, they're sort of the standard basis for polynomials, the most familiar one. So the basis that we're most familiar with. Depending on the context, there are different bases that could be useful. I'll do it here. Let's just look at quadratic polynomials. So polynomials of degree at most 2. That's a 3-dimensional space because it has a basis 1x x squared. Dimension is the same thing as the number of vectors. Okay. This was a space of all polynomials with real coefficients of degree at most 2. So all vectors here are of the form a0 plus a1x plus a2x squared. in this context, sigma, the standard basis, is 1x x squared. Since it has 3 vectors, this is a 3-dimensional space. So dim of the space of polynomials is the same thing as the number of vectors in any basis in it, which means it is 3-dimensional. But here's another basis. Okay. Oh, let's write the matrix representation of any polynomial relative to the standard basis. Yesterday we computed that this is the same thing as the so-called Taylor expansion coefficients. Okay. So if P were A0 plus A1x plus A2x squared, this matrix would be A0, A1, A2. Okay. Here's another basis. I think I'll erase this. This basis that I'm going to present, I'm going to call it beta. Beta for Bernstein or Bézier. This ends up being rather convenient to use for computer-assisted graphics. Computer-assisted graphics. I couldn't sleep last night, so I'm having trouble talking today. It's kind of weird looking, these polynomials. I'm going to have 3 polynomials again. Okay, so it's going to be like this. X to the 0. Okay, I'll write the general form, and then we'll figure out. The general form should be like this. Okay, n, choose k, x to the k, 1 minus x to the n minus k. This is not a matrix. This is this n choose k symbol from combinatorics. So it's an integer given by n factorial divided by k factorial times n minus k factorial. If you're familiar with this Pascal triangle, it's essentially sort of running over Pascal numbers. So in this case, I want to choose n to be 2. And then k is going to be 0, 1, or 2. Okay. So n choose k is going to go from, so it's going to be 1 to 1. Write it here. 1 to 1. These are the 3 Pascal numbers. These are the coefficients. And then k0 gives me 1 minus x to the 2. That's the first basis vector. K equals 1 gives me 2 times x times 1 minus x. And then finally, k equals 2 gives me x squared. This is the Bernstein basis. Okay, I'll write it. There are many other bases like this for polynomials because polynomials are very convenient to use as functions. There's Chebyshev polynomials, a bunch of other ones. Let's try to verify that this is indeed a basis, just to remind ourselves. Okay. You need to know for the exam how to verify that something is a basis. Maybe not for polynomials, for tuples, but the idea is always the same. Okay? Linear independence and span. I'll erase this, we don't need it. So first I need to verify if this is a basis. And once I verify it's a basis, I also want to compute what the matrix representation of an arbitrary polynomial or arbitrary vector here is relative to beta. Okay. Let's call these names. So let's call this beta 1, beta 2, beta 3. Beta 1 of x is going to be 1 minus x squared. Expanding this is x squared minus 2x plus 1. Okay. Beta 2 of x, you see it's a polynomial. Beta 2 of x is 2x minus 2x squared. There's no constant term. And then finally, beta 3 of x is just x squared. Okay? These are the three vectors. You see? These are all polynomials. They're all at most degree 2, which means there are vectors here. These are all in P2. Vectors in this space. What do I need to verify to get that this is a basis? You have two properties. You tell me. Span and linear independence. Span is about linear combinations, and linear independence was about this non-redundancy. Okay. Span. Well, what do I need to do? I need to take an arbitrary polynomial and show that by some calculation that I can write that arbitrary polynomial as a linear combination of these three guys. I'm going to do the calculation in a second, but I want to ask you if you can, just by looking at the forms of these polynomials, deduce that the span has to be everything. Okay. This is an important thing to be able to do. But somehow you need to look at it in a bizarre way. You cannot just see polynomials. You already know that this is the standard basis. Abstract out in your mind that these are sort of functions, whatever. Think of these as vectors. Okay? First vector, first basis vector, second basis vector, third basis vector. In other words, first direction, second independent direction, third independent direction. You see, among all three of these, only the first Bernstein vector allows you to move in the one direction. This one doesn't allow you to move in the constant direction, and likewise this. Okay? And you can similarly argue that, okay, so there is some redundancy here, but you can sort of avoid that and think of this. This allows you to move in the second direction, and this allows you to move in the third direction. So they should be linear. They should be spanning as actually linearly independent also. But let's say that you couldn't see this. Well, you just need to run the whole algorithm essentially. Let p of x, which is a0 plus a1x plus a2x squared, be an arbitrary vector. Arbitrary poly or vector. I want to ask if I can write P as a linear combo of beta 1 to beta 3. I want to solve P of x equals, well, C1 times beta 1 of x plus C2 times beta 2 of x plus C3 times beta 3 of x for C1, C2, C3 scalars. So solve this. And in fact, instead of going for the span, let's remind ourselves this unique representation theorem. Unique representation theorem says a set of vectors or a tuple of vectors is a basis if and only if any vector has a unique representation. So you could immediately say if this expression has a unique solution C1, C2, C3, then the Bernstein basis or Bernstein set is a basis. I'll write it like that so that we remind ourselves of this also. Unique rep theorem. Okay. Beta is a basis if and only if that has a unique solution. I'll put a star there. This equation, that set or tuple of vectors is a basis is equivalent to saying that star has a unique solution. Okay? So how do you figure that out? Well, you just expand everything and equate, right? On the left-hand side, we have P. Left-hand side is P of x, which is what? A0, whatever. A0 plus A1x plus A2x squared. On the right-hand side, I have this linear combo. I'm just going to substitute everything. C1 times this guy. That's what beta 1 is. Plus C2 times the second guy. Be careful with your parentheses. Plus, don't forget the last term, C3 times x squared. Okay, so now we need to expand everything and consolidate. I know ultimately I'm going to have a constant term, a term linear in x, and a term quadratic in x. So what I'm going to do is this. Okay, this is the x squared term, this is the x term, this is the constant term. Allocated memory. Now collect the terms. Okay, C1 minus 2C2 plus C3. That's the scalars next to x squared. Then for x, I have minus 2C1 here, and then plus 2C2. This doesn't contribute. And then for finally constant term is only coming from here, C1. Okay. This gives me a system of 3 equations with 3 unknowns, because left-hand side has to equal to the right-hand side. In other words, this has to equal to this has to equal to that, this has to equal to this. Okay? So we can write it like so. I'll just take my time. Minus 2C1 plus 2C2. C1 equals A2, A1, A0. Oh. I'm asking that is to say, given A0, A1, A2, does this system of 3 equations with 3 unknowns, C1, C2, C3, have a unique solution? Right? That's what I'm asking. Write in matrix form. I'll do it here. After this stage, by the way, I should mention, even though augmented matrices are useful, at this stage, I would suggest that matrix forms are much more useful. So if I turn this into the matrix form, I get this. 2, 0, and then 1, 0, 0. Okay. C1, C2, C3, A2, A1, A0. That was matrix form. Let's do a review here. At this point, can I conclude, without doing any further calculations, that this system has a unique solution? How?
The matrix 1 minus 2, 1, 2, that matrix is invertible because it's a upper triangular matrix, which the determinant is non-zero.
You're almost right. Essentially, this is kind of upper triangular, but the triangularity should be the other way around. That's what we had discussed. What you can do, though, is that you can interchange the first and third rows. In other words, instead of writing A2, A1, A0, you could have written A0, A1, A2. Right? Reorder, in which case this would turn into this, and then minus 2 to 0, and then 1, minus 2, 1. This stays the same. But since a row operation corresponds to left multiplication by some elementary matrix, in order for equality to stay the same, you need to apply the same row operation here. A0, A1, A2. Although it doesn't matter in this case, just for the purposes of answering this question, because at this point, I see a lower triangular, and I know if I have a lower triangular matrix, its determinant is always the product of the diagonal entries. In this case, determinant is 2. 2 is not 0, which means that this guy is invertible, which means that I can send it to the other side, which means that this system has a unique solution. Okay? This has determinant, product of the diagonal entries, not 0, invertible. Okay, so I can send it to the other side and get unique solution. Consequently, this indeed is a basis. Okay. I'll ask one final thing, because we're out of time. What is the determinant of this guy? The determinant of this is 2, so the determinant of this is also 2. Except not, because you're flipping, so you need to pick up a minus. Determinant of this is minus 2. Okay, don't forget that. Okay, we're done for this class. On Friday, we're going to have our second midterm. Thank you.